So good morning again. So today what we'll be doing is going to the second part of the talk, which will be focusing more on the performance and optimizations. So yesterday we just a quick recap what we saw. We took a look at some of the trends. We saw that MPI is the dominant programming model. We got exposed to the MPI 1 and MPI 2 standards and primitives, discussed some challenges, and went with some overview of MVAPICH and MVAPICH2 libraries. So what today we'll be doing is think of, like, let's say InfiniBand clusters are there. Okay, I mean the InfiniBand clusters have been there for 2003 onwards. All kinds of things, SDR, DDR, QDR, all kinds of platforms, Intel, AMD, different kinds of memory subsystems. All these out are there. And then we have the MVAPICH and MVAPICH2 libraries. So it has a lot of different components. And what we'll be trying to basically focus in this talk is to give you a highlight of those components. It will not have time to go over all those components, but see that how those components we have designed and how we have optimized those. Okay? And with respect to those, we'll focus on the performance, scalability, and fault tolerance. I mean, these were the three things which I mentioned earlier yesterday, and the power-aware things we'll put it for tomorrow. Okay, because those are in the future. And at the same time, we'll also try to give you usage guidelines and flexibilities. Okay? Now, before I go into the details, I just want to bring you some examples in real life. How many of you have gone to rental car and rented a car? Okay? I'm sure all of us do. Do you just start driving, or do you do some adjustments? You do adjustments, am I right? Rear view mirror, side mirror, and all those things, because somebody who drove there earlier, he or she adjusted based on their preferences. Okay? If you just start driving that, God knows. Okay? You might be hitting somebody. So same thing happens here. Like, this is a library. Okay? And this library is being used for all kinds of machines and platforms, different compilers, different memory subsystems. So the settings for somebody may not be good for you or for your application, because your application or your user preference might be different than the previous application or the previous experience. Okay? I mean, the same thing happens at home. I mean, so when myself and my wife drive the same car due to something, the day one and day two, we have to keep on adjusting. All right? And the same thing also applies to vendors. You see, a lot of vendors take our library and then deploy. Okay? Now, the question is, are you trying to tune it for different machines? You have to, okay? Because somebody might be using a 16-core environment, somebody might be using an 8-core SDR or DDR. The memory speed might be DDR3 versus DDR2. Everything has impact on performance, because here we are dealing with bare metal performance. Okay, and that is our objective, to deliver you the best performance and scalability. So you have to be aware of all these things, and that's why we actually have, some of you have used, we have a very detailed user guide. It is like a car's manuals. You know, a lot of us don't read it, the car manuals, but when it really comes, you have to flip. Okay, saying, okay, this feature, what does it do? How do I set? So same thing you have to do. We have almost like 100 pages manual, and it keeps on growing with every release, with every features. So you have to go and take a look at those to make sure that you are trying to get the best performance. Okay, so that is the big picture what we are talking here. So what we'll do is we just selected a set of common components, like starting with a job startup, point-to-point inter-node communication, intra-node communication, collective, one-sided, multi-rail support, some of the scalability issues, quality of service, and 3D torus topology, and fault tolerance. So these are some of the things which will focus. Again, there are a lot of other features, and they are again being outlined in the user guide, and we'll not have time to go over all these things. Again, with these features also, we'll just try to highlight the important ones. Okay? So let's start with a job startup. I mean, this is I always give my team members saying that, look, this is like, get into the car, you have to open and start. All right? Then only you can drive. If there are some issues there, you are stuck. Okay? So same thing happens. You have a cluster, you have a library, you have to start the job. And 5 years back, if some of you remember, that was initially the multi-core era was coming, and all of a sudden, systems just went very large. And when people were trying to do the job startup, it was taking several minutes just to launch the job. and everyone was frustrated, saying, okay, what is happening? Because earlier the MPI was treating like a one process. MPI is a process-oriented thing, okay? And it was trying to establish connections to every process. But if you think like there is a node and it has 24 cores, do you need to still connect to each one of them? Okay, and that's what was happening previously, and that used to lead to a lot of communication, a lot of congestion in the system just in the startup. So this is the new framework which we provided that time, and all other MPIs have adopted the similar thing. So we have like a process manager here. So that basically launches the program, and it can also monitor the MPI processes. We basically have MPI run RSH and MPI exec Hydra. There is an MPI exec which is similar to MPI exec.hydra. So these are like the process managers. So you can have like, let's say there are 2 ranks running on compute node A, multiple ranks running on node B, and it can also be used with all the other kind of full-fledged resource managers like Slurm, PBS, all other kind of things. So what we try to do here, this is actually a 2004 paper, if you can go and take a look. We try to change the job startup from a node-centric, from a individual process-centric to a node-centric. Okay, so we wanted to do it hierarchical. So that means if I launch one process within a node, let that process starts launching within the node itself with the other cores. Okay, so like this you can keep on going in a hierarchical manner, and very quickly you can have the entire jobs getting started. So that's what we introduced, some MPI spawn. This can actually, within the node, it can start launching the rank 0, rank 1, and here you can launch rank 2, rank 3, rank 4. And here again, I mean, this happens mostly with the standard TCP/IP, or if you have IP over IB kind of things, because this is the time we have not even established the connections, so the IB doesn't come into the picture completely. Okay, and there again, we have provided some kind of a thresholds and tuning, because you might have only 128 node cluster versus somebody might have a 130,000 node cluster. Okay, again, the same thing will not work for both. So we have given these different thresholds. So here is like, what is we call it like a fast SSS threshold. So the number of nodes to switch to hierarchical launching. Okay, at some level we do flat launching up to a reasonable system size, and after that we change to hierarchical. So for very large scale system, you have to use that parameter. And also when these things are getting launched, so let's say the first one, there is a tree structure. Okay, and as if most of us know, like the tree, you can say, okay, what is the degree of the tree? Okay, so if the degree of the trees are more, then very less number of steps you need. Okay, so here again we have a parameter like a degree of tree is used. The default tree depth, we try to keep it 4. We do some adjustments, but especially if you have a lot of fat node or large number of nodes, you may need to play around with that parameter to see to get the best option. Okay. And here we are trying to show some numbers. So this is just a 1,000 core environment. So this is like a job startup. Even though like even in the 1.5, it was taking around like 5.5 seconds just to start a 1,024 core job. And in our 1.6 version, we have done a lot of optimizations. Now you can see only 2.5. So almost we have cut it down to half on the system size. Okay, and as the system sizes are growing, again, we are always like trying to focus on these parts. So we want to make sure that the jobs get started very fast on these large scale systems. Any questions on the job startup? Okay. So now let's go to the point-to-point communication. So that comes to the basic issues, how we can do point-to-point inter-node and then intra-node. So here we'll talk into a little bit of some of the protocols like eager protocol, rendezvous protocol, and we have a logic called RDMA fast path. I'll go into more details. So MPI treats these messages like short messages are followed with an eager protocol, and the large messages are go through something called a rendezvous protocol. So the eager protocol looks like this. From the sender side, I think yesterday we discussed in the MPI semantics, you just have to send, and then you can actually, the MPI library can buffer it and then send on its own. Okay, so that's what happens. So these go through the buffered approach, whereas if you are trying to send a lot of data, you can go through buffering, but then you need a lot of buffers. Okay, instead of that, we have InfiniBand. We are trying to take advantage of the RDMA and all those features, so we can go through a rendezvous principle so that we don't have to buffer in this. Instead, we just send a request called rendezvous start, we send a message to the receiver saying, are you ready? I am trying to send you a lot of data. That's the rendezvous start. The receiver says, yeah, I'm ready, replies back, then we send the data, and then we send a finish message. Okay? So in that case, we don't have to go through buffers. So here what we have is, for the eager, we have something called the RDMA first path. I'll show you, and then send receives. And the rendezvous, it is unbuffered. And here we have 3 protocols. Okay, again, R put, so that means we are only going through put side, or we can do a get, or we can have a packetized, which is called R3. Okay, so for again all of these, we put something as the default, but you are welcome to try with, because your application might have a different behavior. Okay, the way the program was written. So if you are trying to run that application on your system in a majority of time, it will be good to spend some time to tune it. Okay, and especially starting with earlier, we had this feature in a map is that once you tune all your applications with all parameters, you can put it into a configuration file. Okay, so that you don't have to do it all the time. Once you do it, you save it. Next time you are trying to run, you just use that configuration file. And same feature we have added in the MapIS 2 1.6. So you should be able to do exactly the same thing. So now let's see the eager protocol for short messages. And this used to be a very big challenge. If some of you know, like in the InfiniBand, when it came in the 2001, it was good to send large messages to get good bandwidth. But how do you get good latency for short messages? Okay, because if we go through some rendezvous protocol, it will take a lot of time. Okay, and even if you buffer and eager send, there will be some additional overhead. So we came actually this new design. This was a 2003 paper. It was the most referenced paper in the InfiniBand literature. We first came up with saying that we had a persistent buffer. You can do some memory polling so that sender and receiver knows the sender, if you write it at here, receiver knows that the data will be appearing here. Okay, and exactly you look for that, and if the data is there, that means the data has been received, because we are talking about very like 4 bytes, 2 bytes, and we want to give you a microsecond level latency. And here we have like up to 64 of such connections, and of course there is a buffer. Each one is a buffer, and that's what leads to the memory footprint. Okay, so one has to be a little bit careful here. So we are trying to sacrifice some buffer or memory space to get good performance, and if you just don't use it properly on very large scale systems, your memory scalability will be very bad. Okay, so you have to be very careful here. So here if you see the performance difference, this is on the latest system. So you will see that this is like the send receives, and this is using our RDMA first path. So for very short messages, you can almost cut like a half microsecond out of 2 microseconds. Okay, it's like 25% benefit you get. So this is with the current systems. If some of you remember some old papers like HDR, this gap used to be very big. That's how this scheme was designed. In the very infancy of InfiniBand, send receive was taking a lot of time. Whereas the RDMA, if you go through RDMA and RDMA fast path, you can win. I think the Mellanox people have been trying to close that gap, but still that gap is there a little bit. Okay, so what you can do is here. Got stuck or sorry. So you can try with a lot of these parameters. That's what we give. For example, let's say RDMA fast path, the default is enabled. So we have this as a runtime parameter. So these are all runtime parameters. Okay, so that means you compile, but user 1 or user 2 on application basis, you can just run it. Before you start your job, you can just activate, disable, change. So all these are runtime parameters. So very few are compile time parameters. Okay. So here it is, default is enabled. So for typically we try to set it up to 16 buffers for very large clusters and 32 buffers for small cluster. As very large clusters, we reduce this buffer because we have 64 connections. So we can't really blow up the memory requirement. So here it shows very sample requirements, like our sample usage. You are running some 1024 jobs. You don't have to do anything with here, so don't specify anything. On the other hand, let's say I want to change from 16 to 32. You just say MB2 and now my RDMA buffers is equal to 32. Or if you want to disable, you say 0. So these are very easy. Once you know it, you can just find it out and put it in your configuration file, and you should be ready to go. Okay, so those are the kind of things we have done with all the parameters. Now the rendezvous protocol, so here we have three kinds of protocol I said. So one is the put protocol. So that means we first ask whether the receiver is ready or not, then we send an RDMA put from the sender to the receiver side. On the other hand, we also have an option so that the receiver can actually do a get. Okay, RDMA InfiniBand has the get, so we can try to utilize that. And the other one is the R3, which is packetized send. So that means we have a large message, instead of using the RDMA things, we still do the send receives, but we try to divide it into chunks and then send. Okay, so now you can see that this has a lot of issues with the overlap of computation and communication we talked earlier. Okay, so depending on how your application has been written, okay, so if your sender is trying to send you a lot of data or the receiver side is trying to receive you a lot of data, you can play around with these protocols and see which one is best for your application. Okay, and many people don't do that. Okay, so mostly we put the output, which is the common one used. That's what most of the application use. But I'll suggest all of you, if you are really running or trying to squeeze the maximum performance out of an application, try with all these parameters. You will see there will be a difference. Okay, and once again, we cannot just do it for you because we don't know the behavior of all the applications, so we cannot just change. And it cannot be done also in an intelligent manner. It's very hard. I mean, a lot of people talk about that. I mean, it's like the rental car example. I mean, when can we reach might be another 50 years, I don't know. If the AI and all those technology improve, as soon as you enter the car, it will adjust all these things based on your preferences. Okay, but I don't think the MPI library is at that stage now. Okay, so you have to do some work. So here again, how you change it? So just like the rendezvous protocol, we have a parameter. So default is output. And here it says like the default is output, so you don't do anything. But let's say I want to change to RGate, that's all you have to do. So you have the same things, but just change to RGate and see whether you are getting the good performance. It might be bad, that's fine. Then you know that output is the best. Okay? Or you can do some rendezvous protocol is equal to R3, and then it says like there is a real overlap between, like I think Professor Duardo asked the question yesterday, the data is continuously coming and you are trying to do computation, so that is the mode you want to use. Okay, so again, this shows that we are trying to capture different kinds of behaviors of MPI applications, and one of these behaviors might be best for you, and you have to find that out. Any questions on this? Yes. No, so this finish is, it's a mistake, yeah. So it should be the other way around. Thanks. So now, this is a very common thing. Yesterday, like Sadaf showed a picture, many times you would have seen when you run the bandwidth test, there will be a little bit of kink, okay, at some message size. Okay, let me explain what that means. Many times you will see very smooth number. Sometimes you will see that it will go 12 to 16K, it will drop and then come back. Okay, so why it happens? So here we are trying to show, like we have these two protocols, eager and rendezvous. Eager we are trying to copy and send, whereas rendezvous, either we go through RGate or RPut. Let's say RPut for simplified, we have some additional message exchange, so that means there is an overhead. Okay, so here we are trying to show a number saying for the same data, like for this message size, this is the eager one, and I think the other legend has not come. This one is the rendezvous. Okay, so here you can see if you want to send a short message using rendezvous, there is a lot of overhead. We don't want to do that. Okay, but as the message size increases, so here you will see this is the turning point. Like 16K, our eager is better than the rendezvous, but the 32K, you see the rendezvous is better than eager because the message size has increased. So if I copy, that copy cost dominates and it overtakes the overhead of sending additional messages. And that is the turning point we want to actually control with a parameter called MD2 IBA eager threshold. Okay? And over the years, what is happening is, as things are moving from SDR to DDR to QDR, the cost of sending data over the network is changing, and at the same time, the memory cost is also, or the memory speed is also changing. Okay? Because memory is involved because of the copy cost, whereas the network cost. So there is always this tension between these two parameters, and you need to adjust it on your platform properly. Okay, because that's why there are so many combinations out there, like SDR with slow memory speed, SDR with high memory speed, QDR with slow memory speed, because everybody tries to, if you know, like the large scale systems, when you are trying to configure, it's not always best for the performance because their dollar is involved, right? So you're trying to do a good balance of how much memory I put, what speed I put, versus what speed of the network I put. So there is always these trade-offs, and if you don't do properly, that's what you will see. The performance will go bandwidth, suddenly go down, and then go up. But if you adjust it, I think for the current technology like QDR and with the latest system, it comes around 16K. So every time we make a release, we do some performance tuning on various platforms and adjust it. And earlier, few years back, it used to be 9K. So that number is actually changing a little bit to the right. But again, here we are just showing 16 to 32K. It might be like 18K, 19K, 20K. Again, you can adjust on your system. So, and that's what I said here. Like this can be modified. We have some, like over the last several years, we have put some logic there which automatically detects architecture. So we have a lot of logic to detect it is running on Westmere versus Nehalem versus Magni, what kind of core. So we are trying to make it more automatic, but it's a NP complete problem. The more we do, there are more combinations of platforms out there. So you have to keep on adjusting it. So now let's go to the same issues with intra-node, and that is becoming even more important these days because of the multi-core platforms are coming, and within the core or within the node, again, all kinds of issues are happening. So here, very traditionally, we have like a copy from sender's user buffer to the shared buffer. So that means there are two copies involved. Several years back, we introduced this LIMIC2, which is a kernel-based module to eliminate one more memory copy. And I'll show some numbers here. And using that, we have done like a two-sided as well as like some true one-sided, which is available in the latest release. So here again, just like the earlier eager threshold, there is also an eager threshold here, okay? Because you are also going through the eager and under rendezvous. And depending on like your core and the memory speed, you can actually adjust. So here it is a 16K, and based on the memory speed, this parameter can be adjusted. And the kernel-assisted memory copy, we have the LIMIC module. At the configuration time, you can specify this to activate it. So in fact, the latest TAC Lone Star system, they have actually turned this on, and they get very good performance. If you run some application on the TAC new Lone Star system, you'll get very good performance. And it comes, one of the components is because of this. I'll show some numbers. And here again, you can disable it also. See some numbers here. So this is like a two-sided. And typically, we use this kernel module for large message sizes. And here, if you see, the basic shared memory gives you only 1640 megabytes per second. If you use kernel module, you almost double the bandwidth, okay? Because we are trying to eliminate one copy, okay? The same thing happens also for bidirectional. And then here, you get very good performance because we are trying to not only reduce the copy, but we are also trying to take advantage of the shared L3. Okay, so both the advantages are playing, and then you get, so if your application is in this range, message sizes like 4K, 16K, a lot of applications fall, you'll really see very good boost in your performance. Yeah. It depends again on the platform. Okay, some of the platforms, I'll show some other slides. Okay, this is for the same platform. This is for the same platform actually. Both are for the same platform. Okay. So this is also the same design we have taken, but to do the one-sided. Like yesterday we discussed about MPI to one-sided get, put kind of things, and similar kind of benefits here you will see. Almost you will double the performance. And in this case, again, I'll introduce something called the CPU mapping. And this is creating a very big issue, okay, and a big confusion also whenever you do performance benchmarking. Okay, so let's think of this as a multi-core platform. So this is like 4 sockets. Then it could be a QPI or hypertransport. But the way the systems are connected, your network card somehow is connected to only one of these sockets. Okay, so I'll show you an animation and then it explains the concept. So let's say you are trying to send data from one of these cores, so your data will go into this and then go out, okay? So it will just directly go to the network interface card. But on the other hand, if that core is trying to communicate to another outside the node, it will go through one of the link of the QPI and then go. Okay, so that introduces actually additional overhead. So whenever people are also doing benchmarking from one core to the other core, it depends on which core you use on both sides, and you will get all different kinds of numbers. Okay, so here it shows like some of the numbers. So if I do a core 6 of one node to the core 6 of other node, we saw that gives you the best latency. Okay, on the other hand, if you do like a core, because cores in the socket 1, which is the closest to the network card, so that will have the lowest latency, whereas the cores in the socket 2, so that is in the 8, here you will see that the latency is higher, and then cores in the socket 0, 1 hop from the network card will have in between latency. Okay, just 2 more and then we'll. So with respect to this, not only the performance matters, so now people as a job, let's say you have like 4 cores here, how do you distribute it? Okay, so here again, like we have given some flexibility, like there is a bunch mapping you can do. So that means you have 4 cores, you can run only on one socket, or you can do some scatter. Some people say, okay, I need more memory per core. Okay, so in that case, you can divide it like saying two of these are running on socket 0, 2 are running on the socket 1. So that is called like here we have a scatter. So you can again, to get the best performance, you need to play around with all these parameters, because the underlying communication costs are changing, and depending on how your application was written, which cores are or which processes are frequently communicating with the other one, you have to capture that. Okay, and this is becoming, I mean, if some of you have been doing benchmarking, this is a big issue actually, just to understand how the applications interact with the underlying system. And here it says again some of these numbers. So these numbers are taken with Intel Xeon 2.4 GHz system. So if you see, this is within the node. Okay, in the intra-node we are trying to show. I think there was a question yesterday afternoon session. So if you are communicating with a 2 to 4, you get the best latency, like 260 nanoseconds. Okay, that's the same socket, shared L3, best performance. But if you take the number like 0 to 2, then you see a little bit of increase. So it is a 0 byte and 8 kilobyte. 8 kilobyte, there's a big impact here. The important thing is that core 0, the current Linux modules and all, the core 0 always handles the interrupts. So if you start doing any benchmarking with involved core 0, you'll get bad performance. Okay, so that's what you may see. Somebody might be showing you a number with core 6, might be your number is core 0. So then you will see that they are not good. But if you show numbers like for all different cores, that's what will be the good. And we are actually working on enhancing our OSU benchmark, so that depending on the number of cores, it will show you all the numbers. Okay, in that way there is nothing hidden. So everybody will be standardized. So we'll try to do that. So I think we can stop here. Might be if there are any quick question we can handle, and then continue after the break. And that's why you will see that this hybrid number, like the red line, is always like the best of all the worlds. Okay, and of course this is one parameter we have done. We in the future we want to actually do a lot of intelligence, as I was telling in the earlier before the break, provide a lot of intelligence so that we capture those behavior, and then based on those behavior we can actually try to automatically adjust. But it will take us few years. Okay, and this one is actually support is available only on the MRapid side. It is not yet available in the MRapid 2. This UD and all we are working on. So in some of the future release, you will see this feature. Okay. So now let's move to 2 additional things. One is the quality of service, and then 3D torus topology. Now, there was a lot of discussion yesterday. It has mentioned about like InfiniBand has the quality of service support. This is one of the very important features of InfiniBand. It has like service levels, multiple service levels, and in turn we have multiple VLs. So SLs can use actually different VLs. But most of the time so far, in most of the deployment, people have been using only one VL. Okay, so here what we did is, just like in this area, we always like try to explore, research first, and then see whether it works or not, and then we try to take that into our stack. So what we did is like we tried to ask the question that can multiple VLs help application level. Okay, so that was our objective. So here we introduced a parameter called MV2 use QoS. This support is actually in the latest release of MFS 2. You can also try to use it. It actually distributes traffic across 8 different VLs. That is the default. You can also try to use 2 VLs or 4 VLs, but by just changing this parameter at the runtime. And you will see that very nice improvement, you see. So here, for example, like all-to-all. That is the most dense communication in any MPI application. So here we saw that just the all-to-all latency, this is how if you just use only 1 VLs, compared to that if you use 8 VLs, then the traffic is actually being distributed different VLs, so it is trying to reduce the blocking and is able to make progress faster, and then you get improvement here. So like you get almost 20% benefit just in the all-to-all. And here we try to take an end application, which is a CPMD application. It actually is very much dominated by all-to-all. So here also we see the similar kind of things. At an application level, we can actually give you 11% benefit if you use all the VLs on the system. And here, the way we are trying to show is that through this feature, you can also try to provide differentiated quality of service across the jobs. Okay, so what we did here is that this is only 1 all-to-all. That means in the system only 1 all-to-all is taking place, and the other one is a 2 all-to-all, but no QoS. So that means they are sharing the same virtual lanes and all. So here you will see that the performance is high. But once we do like a with QoS, so that means we separate them out, saying 1 all-to-all goes through some set of VLs and the other all-to-all goes through the some set of VLs. And as expected, like the contention will be lower in the network, and then you will be trying to improve the performance. So this last year in the ICPP, we presented this, and we actually are trying to explore more on the application level benefits of this. Yes, Professor Dot. Yeah. No, so what we have just tried the very simple one-to-one mapping of SL to VL.
But without caring about what's the physical path.
No.
Try to use separate or disjoint physical path.
No, we have not done that. So those are our next steps. So here we started very simple, just saying let's map one SL to one VL. And as a job side, it's much more easier to identify saying this packet will go with this SL, and we are seeing the improvement. Okay. In fact, during the next days, we are working very closely with the TAC people. So in fact, in their Lone Star cluster, after we showed them these results, they have actually turned on the VLs. So we are trying to work with them, really trying to take the user levels numbers and combine it with OpenSM's features of detecting the topology and all. So those are our next steps. Okay. So in the same line, with the same support, actually, now you might have seen like a lot of earlier InfiniBand clusters were only fat tree topologies. Now people are trying to explore different kinds of topology. One important thing is the 3D torus. There is a Sandia, there is a Red Sky system, which uses the 3D. Now the question is 3D somehow InfiniBand doesn't match because the 3D topologies, especially 3D torus, has a lot of deadlock issues. Okay, even before even InfiniBand, when wormhole routing and all were there, I mean, Professor Duardo is sitting here, he has done a lot of research on this deadlock freedom. So you have to come up with the best routing scheme, which is deadlock free on those topologies. So one way to do is being done in the InfiniBand context is that you can actually use different kinds of service levels. Okay, so that you separate the traffic and then break the deadlock pattern. So the same SLVL principles can actually not only give you QoS, but it can also help with the deadlock freedom. And there are like new routing algorithms have been introduced in the OpenSM. It can use actually multiple VLs to route messages in conflicting paths. But now the question is, when you are launching an MPI job, how does the MPI know that, okay, I'm sending, like I'm going east or I'm going west, I'm going north, west on destination, what SL and VLs we need to pick up, okay? Because otherwise you'll put the system into deadlock if you don't pick these things correctly. Okay. So what we have done here is that we worked closely with Mellanox people and also Sandia people. So this is the first cut solution we have. Then again, we are trying to enhance the solution. So query the OpenSM and retrieve a path record for source destination LID pair. So this is with the OpenSM. There is some solution has been done for each and every source destination pair. It shows the path record, shows which SL to use, so that in the system, even if everybody is communicating with everybody, there will not be any deadlock. Okay. And so then we use that SL specified in the path record, and we have provided some runtime support here, enabled by default at the configuration time. So for 3D, you just say enable 3D Torus support, and then you can make it on and off. You can do some retries. So all these features we have added. So now you can actually run MVAPIS 2 on any 3D Torus system. So in fact, Red Sky people are actually running it on the past month with MVAPIS 2. Okay. Any questions on this part? People didn't have a lot of coffee, or okay. I'm sorry, a slide here. Okay, so then final portion I want to focus is on fault tolerance. I talked about that yesterday, saying fault tolerance is becoming very, very important because we are talking about commodity systems, commodity components, and we want to make sure that we provide reliability and on fault tolerance. So we have a bunch of solutions in the MVAPIS and MVAPIS 2 stack. So we categorize them into two things. One is the network level fault tolerance and resiliency, and the other one is the process level fault tolerance and resiliency. Okay, because these two are orthogonal, because errors may happen, or links may fail, switch may fail, and the other one is the process may fail, or the nodes may die, kind of things. So we have a lot of solutions, but I'll not have time to go over all these things. I'll just highlight these three things. One is a network level fault resilience, enhancing checkpoint restart performance with some IO aggregation, and then proactive migration. So network level fault resilience. So currently, if you see that MPI jobs typically abort if there is a failure in the link or adapter in a switch. Okay, so let's say you are running a job, switch fails, job gets aborted, and it again goes back to the scheduler. You repair the system and then gets resubmitted. So, and that of course wastes time. It impacts the productivity. So the question we asked is that, can we stall a job instead of aborting it while the failed component is fixed? That means you may need to reboot the adapter or reboot the switch. So here we worked the solution. So this work was jointly done with Mellanox. So it can protect against various network failures like switch reboot failure, HCA failure, or even congestion. So there is a flag here. We call it network fault resilience. So you just need to turn it on. Okay, and with that mode, it takes care of this feature. By default, it is turned off because some people don't want to use it, but you can turn it on. And this feature is again in the MVAPIS 1 side. It's not there in the MVAPIS 2, and we are trying to move it to the MVAPIS 2. The other kind of thing, which is a process level fault tolerance. So that means what happens if you are running very long running application, then there is some error or a node error, node temperature went up, the node died. And the standard solution people have used is the checkpoint restart. Okay, whether you do systems level or you do applications level. Okay, of course there's a lot of debate, is that the scalable solution or what is the alternative? So here we have been working along this line for last several years. So what we did is like almost for last 5 years, we have a fault tolerance checkpoint restart support using the Berkeley Lab checkpoint restart. So they do checkpointing on a single node, but we extend that for the MPI level. Okay, for the MPI level, it is a little bit tricky because you have to suspend all connections to take a consistent checkpoint, and then store the checkpoint, and then after that, you again take the checkpoint and restart. That is the standard solution we had, but the performance was not good. So then we tried to take a look at, just like the previous slide we saw with respect to multi-core, can we take a similar approach, like just like we enhanced a lot of collectives, can we also enhance the checkpoint restart? Okay, so this is the scheme which we call IO aggregation. So currently what happens is on a node, if there are 24 cores, everybody is trying to write data, the checkpoint restart. So the NIC interface becomes congested, and the file system also becomes congested. So what we did is did a lot of analysis. We have a bunch of papers along this line. I don't want to go over those, but just to show that a lot of these messages we can aggregate. We can define some buffers. So put all these messages and then send it as a big message to the file system. Okay, and in fact, if we do that, I'll just fast forward and show you the performance improvement. So this has been done with 4 sockets Barcelona systems, like 16 cores or 16 processes per node. You'll see the CR time, checkpoint restart time, we are able to improve by a factor of 12, 13, 14%. This factor, okay? By factor of 13 or 14, we are reducing. So what it means that you can use these schemes and take your scalability. Like earlier, if you were saying that, okay, on these many X number of cores beyond, you cannot use CR or your file system cannot handle, we want to improve it by a factor of 13 or 15. And as in future, if we'll have more number of cores per node, like all these 64, 96, 100, 200s are coming, so it means that we can actually scale the CR to those large scale systems and to reduce to increase the MTBF. And to do this, these are very simple. Again, we have a lot of runtime parameters here, just to see, okay, use the aggregation. You can define the buffer full size or chunk size. These are some internal designs. You can specify, like, okay, I'm putting 16 megabytes of memory for this buffer full. In what chunk size we write. So this is like showing a sample example so that you can activate this. So that is one angle which is a lot of people are using. But then we are looking forward to the next level of solution, which is really exascale level solution. So checkpoint restart, yeah, you can increase up to a certain extent, but if somebody asks, like saying, okay, there is a 1 million core system, will the checkpoint restart work? My answer is no, okay? But the advances are happening that these days, there is a lot of support. You must have heard of IPMI support. This is the intelligent performance monitoring environment through which you can actually find out a lot of information, like the node temperature is rising, or your disks have started running like faster or slower, memory corruptions are happening. So these are the signs that this node is going to die. Okay, it's just like, I mean, before we fall sick, we get some symptoms, the sneezing, cold. So that means we have to make an appointment with the doctor, okay? So same thing happens. You can get a lot of information from the IPMI. Then the thing is, if we get that kind of information and the probability of these nodes are going to fail is higher, can we start migrating? Okay, provided we have spare nodes. Okay, and this can happen on a node basis or a blade basis or a server basis or a rack basis. You can define your granularity. Okay, as long as you have spare, like a blade server, you have a spare, there might be like 32 processes running here, so you can migrate that. Or you can specify rack as a default, and then you can move the rack. So you can do it at any granularity. Okay, and if you do that, then what happens is this is like a proactive migration. So that means we are trying to, before even system fails, the CR helps you after the system fails. Like you go to the doctor, get some antibiotic, and you recover. Here, before that, you start taking some medicines, and then don't even have to go to doctor and don't go to the next level. Okay, so that's what we are trying to provide. Here again, we try to do, so it's a job, pause, and process migration framework, and this is already in the MAPIS 2. People are using it. So the idea is that as soon as you detect that this node is going to fail, we actually send a signals to all the other processes saying pause, because this one is trying to move. Okay, so we pause for a brief period of time, do this migration here, and there are a lot of techniques here, copy-based, RDMA, and all, and then we go there to the spare nodes and then get restarted, and then all the processes again connect back and continue. So this feature is already available. You can actually do the same kind of thing. Example I said, this is actually, excuse me, has been done, something we are involved in with a big consortium called Fault Tolerance Backplane. Some of you might have heard of this. We are involved there. So it actually utilizes that support. And you can exactly say, trying to do some aggregation, buffer full, chunk size, etc. And if you see the performance here, we had a paper last year at Cluster. So here it is trying to show how the migration performance compares with a checkpoint restart. This is with the PBFS. This is with the XT3. So we can cut it down the time, okay? The idle time, like the pause time by a factor of 5 or 4.26 here on different kinds of system. And here it shows like how much data is moved, like a CR, because every process data you need to write to the file system, whereas here only subset of processes which are going to fail you need to do. So that is a significant benefit in terms of the data movement, and this is where the benefits are coming. Okay, and now actually we have another scheme, which is we have done some pipelined RDMA migration. So that means even the migration, instead of putting it at the completely as a big data, you try to do some pipeline operation starting from the sender to the receiver, and that's even cuts down the time. So we have a paper at the CC grid coming up, so this number goes to a factor of 10. kind of thing. So we can improve to make it much more practical. So that on very large scale system, you can actually try to utilize these. And we already have some internal designs working with IPMI integration, so that is not available to the outside yet. We'll try to make it available in the future releases. So if you have IPMI environment set up, you should be able to utilize this migration. Any questions so far? I think this is the last slide, so I'll conclude. Okay. So what we showed here again, this talk that both MVAPIS and MVAPIS 2 has a lot of these performance